Hi everyone, today, we are going to learn about the experiment on LVDT, which stands for Linear Variable Differential Transformer, used for displacement measurement. Step 1. Project setup in LabVIEW. First, open LabVIEW software and create a new project folder. Give the folder a clear and suitable name. Once the project is ready, go to the front panel. On this panel, select the generation mode, the excitation frequency, and the output measurement channel of the cDAQ, which is connected to the LVDT sensor. Now, set the excitation voltage to the primary winding of the transformer. This provides the required analog signal. Then, select the sensitivity value of the LVDT sensor. Step 2. Filter configuration. The most important step here is to configure the IIR filter specifications. Why? Because the filter helps suppress noise that occurs in the analog system, mainly due to changes in magnetic flux in the primary and secondary coils. Choose the topology of the filter. For this experiment, we use a Butterworth filter. Select the type as low-pass filter, and then define the cutoff frequency. Step 3. Data acquisition. After all the parameters are entered in LabVIEW, specify the actual position of the LVDT core. Start with a displacement of 20 mm and gradually reduce it to 0 mm, step by step. Each time the position is adjusted, begin the DAQ, or data acquisition process, and record the values. When the measurements are complete, click on Analysis Completed to finalize the dataset. Step 4. Graphs and tabulation. At this stage, you will see the graph of excitation and the measured values of the LVDT. The table should include the following parameters: actual displacement, measured voltage, ADC count, and the measured displacement of the LVDT. Copy these graphs and paste them into a Word file, just like we did earlier in the vibration measurement experiment. Now, for each actual position of the LVDT sensor, plot the graphs and prepare a tabulation. Step 5. Result. Finally, plot the graphs of actual displacement versus all other parameters. The curve that appears is a distinct V-shape, which is the characteristic response of an LVDT sensor. This confirms that the output voltage of the LVDT varies linearly with displacement, positive in one direction, negative in the opposite direction, and almost zero at the null position.
Short conclusion. The experiment proved that an LVDT, linear variable differential transformer, can measure linear displacement accurately with both magnitude and direction of motion. The output voltage varied linearly with core displacement, positive on one side, negative on the other, and nearly zero at the null point. Using LabVIEW with cDAQ, the data was filtered, recorded, and plotted, forming the characteristic V-shaped curve of the LVDT. This confirms that LVDTs are highly sensitive, precise, and reliable sensors, widely used in automation, monitoring, and control applications.
If you have any doubts and need clarification, kindly ping me in comments. Thank you.